This black hole shouldn't exist, but it does. In 1974, Stephen Hawking sat down and calculated something that should have been impossible. He proved mathematically that black holes, objects so gravitationally violent that not even light can escape them, are slowly leaking, sending particles outward, radiating energy into the universe from beyond a boundary that, by every prior understanding of physics, nothing could ever cross. It was the closest thing science has ever produced to receiving a signal from inside a black hole. And what that signal is telling us may be the most profound discovery in the history of human thought. Because the message is not just about black holes, it is about the nature of space, the nature of time, and whether the reality we think we are living in is actually the fundamental version of the universe, or something that emerges from a deeper layer of existence that we have not yet learned to see. I went through the research of Professor Brian Cox, the work of Stephen Hawking, and the latest papers in theoretical physics to break down exactly what black holes are revealing about the structure of reality itself. Stay with me, because the last thing this research suggests will permanently change how you think about what space and time actually are. Start with what a black hole actually is. Because most people have a picture in their head that is close, but missing the detail that makes everything else make sense. The idea goes back further than most people realize, all the way to the 1780s. Two thinkers working independently of each other arrived at the same concept through a single elegant question. The Reverend John Michel in England and the French mathematician Laplace both began thinking about escape velocity, the speed required to break free of a gravitational field completely. From Earth's surface, that speed is about 13 kilometers per second. From the surface of the Sun, it is around 600 kilometers per second. The heavier and denser the object, the higher the escape velocity required to leave it. Their question was simple: what if you kept going? What if you imagined a star so massive, so compressed, that the escape velocity at its surface exceeded the speed of light? Then nothing, not matter, not radiation, not any signal of any kind could ever get out. You would have an object that exists but cannot be seen. An invisible star, a dark body. That intuition sat dormant for over a century until Einstein's general theory of relativity gave it mathematical teeth. What Einstein showed was that gravity is not a force in the traditional sense. It is a curvature of space, and time itself mass bends the fabric of reality around it, and objects follow the curves that bending creates. A black hole is what happens when that bending becomes so extreme that space and time are distorted beyond any prior description. And here is the detail that stops people cold when they first truly understand it. The event horizon, the boundary surrounding a black hole, the line beyond which nothing returns, is not simply a dangerous region. From the perspective of an outside observer, it is a place where time itself stops. Not slows, stops. This is a direct, unambiguous prediction of Einstein's relativity. Look at the event horizon from the outside, and you are looking at the end of time as we understand it. Cross it, and you are not entering a dangerous place. You are entering a region where the ordinary rules of what space and time mean have ceased to apply. At the center, what physicists call the singularity, the situation becomes even more destabilizing. It is tempting to think of it as a point in space, but as Professor Brian Cox explains, in a fully correct mathematical description of a black hole, the singularity is not a place at all. Space and time are so violently distorted that their roles effectively swap. The singularity is not a location you travel to. It is a moment in time. It is the end of time itself. And we have no physics, none, at all capable of describing what that actually means. For decades, that was where black hole physics essentially stopped. The singularity was a mystery we could not approach, and most physicists quietly accepted that it might remain permanently beyond understanding. Then, Stephen Hawking changed everything. In 1974, Hawking published a calculation that combined two theories: general relativity, which governs the very large, and quantum mechanics, which governs the very small, and applied both simultaneously to the region just outside the event horizon of a black hole. What emerged from that calculation was a result so unexpected that it initially seemed like a mistake. Black holes glow. They emit particles. They have a temperature. This phenomenon is called Hawking radiation, and the mechanism behind it requires a brief detour into quantum mechanics. At the quantum level, empty space is not actually empty. The vacuum of space seethes constantly with what physicists call virtual particles, pairs of particles that flicker into existence together, one with positive energy and one with negative energy, and then annihilate each other almost instantly, returning to nothing. This process happens everywhere, all the time, throughout the universe, and under normal circumstances is completely invisible and consequences-free. At the event horizon of a black hole, the geometry of space is so extreme that something different can happen. One particle of the pair falls inward across the horizon. Its partner, now separated from the particle it was supposed to annihilate with, escapes outward into the universe. To compensate for the energy that escaped, the black hole loses a tiny amount of its own mass, and over an incomprehensibly long timescale, trillions upon trillions of years for a large black hole, this process continues until the black hole has radiated away all of its mass and disappears entirely. Black holes are not eternal. They have a lifespan, and at the end of that lifespan, whatever they contained is returned to the universe in the form of Hawking radiation, which is where the signal comes in, and where physics runs directly into its most unsettling, unsolved problem. There is a principle woven into every law of physics we have ever discovered. Information is conserved. It cannot be destroyed. This sounds abstract until you think about what it actually means. Take any physical object, a book, a human being, a star, and destroy it completely. Incinerate it, vaporize it, break it into its most fundamental components. In principle, if you could collect every single particle, every quantum of radiation, every photon that resulted from that destruction, and track them all with perfect precision, you could reconstruct the original object. Not in practice, the engineering required would be impossible, but in principle, in the mathematics of physics, the information is always still there. Nothing that exists can be truly erased from reality. Black holes appeared to violate this completely. If a black hole consumes information, a book, a star, a civilization, and then eventually evaporates into Hawking radiation, what happens to the information that fell in? The radiation that escapes is generated at the event horizon, not from the interior. It carries no apparent imprint of what the black hole consumed across its entire history. The book, the star, the civilization gone, erased from the universe. This became known as the black hole information paradox, and for decades it represented a fundamental crack between quantum mechanics and general relativity. The two greatest theories in physics were producing an irreconcilable contradiction. One said information is always conserved. The other said black holes destroy it. Both could not be simultaneously true, and neither was willing to give. For decades, scientists thought black holes destroyed information forever. But newer research suggests something far stranger. Black holes may actually preserve everything they consume. The clue lies in Hawking radiation, tiny particles slowly escaping black holes over unimaginable timescales. This radiation may not be random. Hidden inside it could be an incredibly complex record of everything that ever fell in. In theory, if someone collected every particle emitted across trillions of years and had an impossibly powerful quantum computer, they could reconstruct the black hole's history. But the deeper mystery goes beyond black holes. To explain how information escapes, physicists are exploring an idea called quantum entanglement and something even stranger, emergent spacetime. The idea is that space and time may not be fundamental at all. Instead, reality itself could emerge from deeper quantum connections beneath what we experience. In this view, black holes are not just cosmic monsters. They are cracks in physics, places where our understanding breaks down, forcing us to ask one of the deepest questions ever. What is reality actually made of? If this changed how you think about space, time, and reality itself, share it with someone who thinks black holes are just objects that suck things in. And watch this next. It covers what quantum entanglement actually is, and why it suggests the universe is far stranger than any science fiction ever imagined.